Okay, well, let's try to make some calculations and see what we can do. Just a reminder that what we had here was a linear function, and what we wanted to do was calculate the slope of a chop, but not a due east-west chop or a due south-north chop, but a chop in any direction. The slope is always going to be rise over run. Now, when we're talking about functions of two variables, the rise is just delta z. It's a change in the height. The run, well, if I was going sideways, it could be delta x or delta y, but what I need here is the actual distance from this point to this point. What I'm going to do is just make a little right triangle. This right here should be delta x. This right here should be delta y. And so the run should just be something like the square root of delta x quantity squared plus delta y quantity squared. Now, that's what it would be if it were linear. If it were almost linear, what would change, right? So if it was locally linear instead. Well, the only changes that we'd make is that the slope would be approximately equal to delta z over the square root of delta x squared plus delta y squared. Now what I'm going to do is just carry this calculation up to the very top, and we'll do some stuff with it. Not some major stuff. So the slope we're looking for would be estimated by delta z over delta x quantity squared plus delta y quantity squared. And now what we're going to do is use a differential, as I promised. What we're going to get here is we remember that delta z looks like fx delta x plus fy delta y. Just like that. This is all over delta x quantity squared plus delta y quantity squared, like that. And now we start to bring in the linear algebra. One thing we want to be able to do when we see something that looks like something times something plus something times something, that's a dot product. That's always got to be at the back of our mind somewhere. This is the dot product of the following two vectors, fx, fy, and those are just the partial derivatives in each direction, dot with delta x over delta y. So that's just a vector that actually pointed from the first point to the second point, all divided by, I'm going to put it over here because it doesn't matter where I put it on the bottom, delta x quantity squared plus delta y quantity squared, like that. Now this function actually has a name. I mean, that vector there, it's called the gradient. We'll talk a lot about that in the next two lectures. Meanwhile, the notation for the gradient looks like an upside down delta, like that. But this is just the vector you get when you take the partial derivatives and make a vector out of it. What in the world is that? Well, we know that delta x delta y was the vector that pointed from our point in the direction of where we are chopping. Now what happens when you take a vector and divide by its length? You get a unit vector. So this is a unit vector that's pointing in the direction of the chop. And so this is our formula for the chop, for the slope of the chop in any direction. It's actually called the directional derivative for that reason. So it's not a partial derivative, it's a directional derivative of the function at the point in the direction of u. And remember, u has to be a unit vector. there. And since we actually started with approximately equal to of there, we're okay with this being nonlinear. Because the better this gets better and better, the smaller delta x and delta y gets. And when you take the limit, we get actually what we have right here. And that's really pretty cool. So that's going to be our formula for taking the derivative of a chop in any direction.